Hi class, I put together a video to help those of you to complete this lab. It could be a little complicated, it's not difficult, but it could be a little complicated in a few areas. So empirical formula, the easiest way to understand empirical formula, I was telling some other students, is that it is pretty much the skeleton, the foundation before you build up. So if you had to think of it like a human body, the empirical would be the skeleton and the molecular would be everything else. So some compounds all start with empirical. So they all start with the same skeleton, but as they become molecular, they change into something else. We all have the same skeleton, different sizes, everything else, but it's a skeleton. And then the molecular is everything that makes us all different looking on the outside. So empirical is the simplest whole number, no fractions, has to be whole numbers. And the formula of a compound expresses a possible whole number ratio of subscripts of the elements. So if you have a fraction, you have to make sure you get those to the whole number and you multiply everything in the compound. The molecular formula represents the actual number of atoms. So when you're working with a compound, the molecular formula is what you would normally be working with, not the empirical. Molecular formula is, there's a formula here you can see, the empiricals here in parentheses, and you multiply it, and that would give you the molecular formula. So I have an example here. The 6 is multiplied by the carbon. The 6 is also multiplied by the hydrogen, and that gives you the molecular formula, but the empirical begins with the CH. And here's just some examples for you to see. More examples where the molecular formula, all these are very different compounds from each other. However, they all have the same empirical formula. So they all start with the same foundation, the skeleton, and they built out into something different. Ionic compounds are always empirical. There is nothing to reduce down. They will always be the lowest whole number ratios. Why is the term molecular mass inappropriate for sodium chloride? It's because it's an ionic compound. So we tend to get lazy and refer to everything with molecular mass, but it technically would be a formula mass or formula weight. I put up an example here. It doesn't really have to do with the lab, but just to understand how to break down some of these problems. So this is something you can go over on your own. In the lab, you would normally be doing determining the empirical formula in two different ways. There's three, but we're not doing the third one. You have a bicombination reaction, which you would be completing if you were in person, and a decomposition, which we also have listed in this lab. The third one we're not going to cover. We would not be doing this one. In the lab, we have a few parts. Part A is you prepare the crucible, so you need to read and follow the directions for this and how to prepare the crucible to be heated for this lab. And here's an example of what it would look like if you were actually in the lab with the tongs still holding the lid here. Part B, you have a combination reaction dealing with magnesium and oxygen. Part C, you have a decomposition of a pure compound, producing calcium oxide as a product. Part D, you have a combo reaction again. So you have two combination reactions and one decomposition reaction. You will have calculations that you have to incur. These are taken right from my slides from lab. So they might be a little different than what you are actually doing as an experiment for INTIS. Keep in mind, and this is where I have it at the bottom, that he may change things on Canvas. I am presenting to you the slides that I have done. So here's an example of a decomposition reaction. In a decomposition reactions, a single reactant breaks down into two or more products, and here we have an example of that. A student heats 75 grams of an unknown compound to produce oxygen, which would be a gas, and 45.6 grams of potassium chloride. What is the empirical formula of the unknown? So first of all, this is a decomposition reaction. You need to understand that it's going to break into two or more products. In this case, it's two, but we don't know what the compound is. So it's very easy we have been given enough information, we would be able to figure this out. We were given the amount of the unknown compound, and if you see on the side, I tend to write things out underneath in an equation form so I can see what I need and I can see what I'm missing. So I don't know what this compound is, but I know that it involves all of these elements. So I could also put here KClO and just with a question mark of what it would be. So we were given the mass of chloride, potassium chloride, and that's 45.6. This is our product. So we now have the mass for our unknown compound and our mass for one of the products. Because of law of conservation of mass, nothing is created nor destroyed. We would know that whatever is on one side regarding mass-wise will be matched on the other side. It has to balance. So through simple subtraction, we can figure what this is. So we would deduct 75 grams minus the 45.6, and that's going to give us 29.4 grams of mass of oxygen. There should be a 2 here. That's a mistake. So here is 29.4. We now have all the information that we need in order to do this. We don't work in grams. We do to a certain point, and after that, everything needs to be changed to moles. So in the second step, change everything to moles. So here, we use the molecular mass, and we get the moles of potassium chloride. Here we use oxygen. This is a mistake. This should be a 2 here on these slides. I apologize for that. So this should be 2. That's where the 32. This also should indicate that it's a 2. And it's going to give us a mole for that. We get the mole ratio and set this up. And there's a 1 and a 1.5. So you multiply to make sure that you have it. So I have for a ratio of for every 2 potassium chlorides, we have 3 of oxygen molecules. Then from there, we can get the percent by mass of these compounds and what is produced from the reactant. So we take the mass of potassium chloride, which is right here, and set it up over the total mass of the unknown compound, and what is produced is 60.8%, and the oxygen, this should be, I think, flipped as well, is 39.2. You don't have to do this because once you have one, you can subtract it to get the other, but I always do this just to be on the safe side and make sure that my math matches up. After that, you can figure out what the compound is. These tend to match up. They might not always match up, but honestly, it wouldn't be that difficult, and I realize everybody's on the internet to figure out what the compound is and balance an equation. I don't know how intricate Entis wants his stuff, so I'm, again, giving you my slides and how I do stuff. He likes to move numbers around, and sometimes to see if you can catch mistakes, catch certain things. I do not know what he has done on his. Again, I don't have any say on Canvas, and I've agreed not to go over in detail anything on Canvas with the students. He wants everybody to do it independently. So keep in mind, these are from my slides in my class. Determine empirical formula from a combination reaction. In a combination reaction, we have 2 or more reactants, and they combine to form a single product. A student burns 12.3 grams of magnesium to produce an oxide. And when it means oxide, it means it's going to be a magnesium oxide that weighs 20.4 grams. What is the empirical formula of the oxide? So here again, I put up a formula, an equation. It's not balanced, and it's not going to be balanced. I'm purposely not balancing any of these because then you can't go back and say that I gave you wrong information. No, I did not. Entis might change this stuff. This is from my lab. I will have to keep saying this because students sometimes don't want to hear what I'm saying. So again, I put out an equation and I put the mass of what I've been given underneath so I can see what I need and what I don't have. Or what I have, I mean. So next step, grams. Change grams to moles, and that should give you enough information to proceed. So on this one, I didn't make the mistake. I put oxygen, 2 oxygens, so I have my moles. After that, we can, now you are going to always divide by the lower one, the smallest one. So we did that here. This gives me 2. This gives me 1. I can now put out my, plug these in, and that gives me 2 magnesiums and 1 oxygen. Here we take the molar mass, and we get the percent of magnesium in this, and it gives us 60.30, and over here it gives us 39.70. That should equal 100 or close to 100. It should be somewhere, if it's not like this is, for instance, 99, but actually, no, it's going to be 100. I didn't pay attention to the other part. Disregard that. Anyways, it should always equal 100 or close to it, and it usually has to just do with some rounding. And a balanced reaction that I have not done. I don't know what he wants on his, so that's why I purposely try not to give too much information if it doesn't match his. percent by mass. This looks really blurry, but I took this right out of the actual PDF that Entis had posted, and this just gives an example of where I got the percent mass and how to break it down. I strongly suggest you read the lab several times to understand fully what's going on in this lab. Again, it's not difficult, but it can be time consuming, and you can feel really lost if you're not giving it your full effort. This is straight from this page. I just broke it down into another slide so you can see, and as you see, I use Google Docs or Google Slides, and I move these to PowerPoint, and it's kind of messed all my stuff up. So these slide over, and these slide over, and this slides over. I didn't check this page. Anyways, this is part of my lab. These are just warnings that I give my own students when we are actually in lab. And then this is an extra problem that is not a part of the lecture or lab, but you might have problems like this. I'm not sure what Entis gives you, but this is just an easy problem that you could look over and see if you get. So that is it. That is the actual lab. I have given this sample of a decomposition reaction. I have given you a sample of a combination reaction. In this lab, you have 2 combination reactions and 1 decomposition reaction. So you have all the skills that you can to come across and finish these, at least based on the samples that I've given from my lab. You should be able to complete this lab with some effort. Okay, thank you for listening to my lecture if you guys are watching this, and that's it.